So, hi everyone. It's great being with all of you here in this new webinar about formal verification. Today we have a formal verification webinar with Shoham from our team. The idea is for you to get prepared for the Uniswap contest starting on September 6th on Cantina. So if you have any questions, if you want to learn more, get ready and be prepared for this amazing webinar that we are hosting this Monday. So I will give the microphone to my friend Shoham, who is starting in just a few seconds.
Okay, so thank you, Fiorella. So my name is Shoham. I work for Certora, and today I'll give this basic tutorial about using the Certora Prover. Before we start, let me share screen with you. So we have a lecture notes. We've posted the link to the lecture notes on the chat. So in the lecture notes, you also have some useful links. One of them is the code repository, which we assume that you've already cloned. If you have cloned it, probably you should update it. I mean, git pull, because I've made some changes this morning. And there's the Prover installation instructions and the documentation and the Prover tutorials. We are assuming that you've managed to install the Certora Prover and have a key. But if not, you can always ask in the chat, and our team here is available to try and help you out. Okay, so let's start. So I'm going to start fairly slowly. And we're assuming some very basic knowledge of Solidity, but really not too much. So we're going to start with a simple voting contract in which a user can simply decide to vote if they're in favor of something or against that proposal. So, the first thing we want is to prevent people from voting twice. In order to do that, we'll have a mapping from address to Boolean, which tells us if the given address has already voted or hasn't voted. So we'll give it a nice name, has voted, and that tells us if somebody already voted or if they haven't voted, and then they can vote. And then we'll need a couple of integers to count how many votes we have in favor. So votes in favor, and we also need to count how many votes we have against. So votes against. So these are votes in favor of the motion, votes against the motion, and now I'm going to do something which is it's an anti-pattern in a sense, but let's do it anyway. We'll have a variable counting how many total votes we have. And this contract needs just one function, which is vote. And the user tells us whether they are in favor or against. We'll make it external. So external means that someone or something outside the contract can call it. And then obviously we're going to require that this user has not voted before. So the user, if you're not familiar with Solidity, the address or the person or contract that sent the message that called this function is given by MSG sender. This is the identity of whoever called this function, and we require that they have not voted before. If this requires not satisfied, the computation reverts, meaning it goes back to the start of the transaction. everything rolls back. It's as if it never happened. And the first thing we do is obviously we mark the message senders if they voted already. So that will be true. And then we do the obvious stuff. So total votes is increased by 1. And then if they are in favor, then votes in favor is increased by 1. And otherwise, votes against is increased by 1. And that's it. That's the entire contract. And this contract that I just wrote, you can find it in the repository under SRC and then voting.so. So this is the contract. And now we want to, if we want to verify this contract, what we do is we write a spec. So a spec is a file with whose suffix is SPEC, spec, and we write it in CVL, which is the Certora verification language. So let's just write a spec. There's no need to talk and not write. So Certora specs voting.spec. Okay. So in this spec, we'll have a rule. The syntax of the CVL follows very much, is very similar to Solidity, but not completely. So if whenever we run into some differences, I'll alert you. So let's call this rule vote integrity. And we'll have a parameter is in favor. And then what we're going to check is that the function vote actually works properly. So we have the number of voted before, which is the total votes. And then we're going to call the function vote with this parameter, whether we're in favor or opposed to the motion. And then we're going to assert that the number of total votes increased. So total votes is greater than votes before, and we can add some message, what should really happen. And that's it. This is the spec. Well, almost. So once we run this spec on the contract, the prover will try to check whether this assertion is always true. And if it discovers that it isn't, if it finds a counterexample to this assertion, we will see the actual example as a call trace of the call. But before we can continue, there's something I've glossed over here. The real question is, who is voting? So in the contract, as you can see, the person voting is the message sender, but we haven't specified the message sender here. So what happens is in CVL, we have a new type, a type called env. This type encapsulates all the environment data that you get in Solidity, which is, for example, the message sender, the message value, which is the amount of Ethereum you sent over, the block timestamp, also sorts of value like that. And this stuff is encapsulated inside the environment. And here I simply declare E to be some arbitrary environment, or as far as the prover is concerned, any environment is possible. And so in this case, the e.msg.sender is the address of the message sender. Now, but I have to somehow pass this argument to the function. And the way we do it is the first argument in any function is the environment. So we always have to give the environment variable in every function. And this is true also for total votes. Yes, we have to give the environment variable. However, this becomes a little bit cumbersome and inconvenient. So we have a way to declare that functions are independent of the environment. So certain functions do not care at all about the environment. Let me just add send out. And the way we do it is like this. We declare the getter. So the getter of total votes is total votes. It's external, and it returns a uint 256. We declare it to be env3. Its value is irrespective of the environment. And once we declared it, we do not need to use to add some environment variable here or here. Okay, so this is the spec, and we can run it now on this contract. But before we run it, we'll go quickly over the config file. So the spec itself you can find under Certora specs voting bug. Okay, so this is the spec we're going to use. And then in order to run it, we need a config file which will give all the parameters to the Certora Prover. You can also pass all these parameters in the command line. It's inadvisable because after a while you get into a lot of parameters, setting up the entire scene of all the contracts that you're going to need. So let me just load up the config we'll be using. It's under Certora conf and then voting bug conf. So the config file is simply a JSON5 file. The difference between JSON file and JSON5, as far as we're concerned, is simply you can have comments in JSON5 files, which is nice. What we have here are the files. These are what we call the contracts in the scene. So in this case, we'll be using a slightly different contract than this one. We'll come to it in a second. And we have the name of the file, the path to the file, sorry. And then we have the name of the contract we want from this file. And then verify the name of the contract, the main contract we're going to verify. By the end of the tutorial, you'll see cases where there are multiple contracts, and one of them is the main contract, or what we call the current contract. And this is the spec we want to run on it. And then some message, because once you run a lot of, you make a lot of runs, you tend to get confused by them. So you want to differentiate between different runs. I don't know what sort of setup you have for the Solidity compiler. If you have a particular path you want to use, then you can use here solc and the path to the compiler, or you can add it in the command line. If you've been using solc select, then you need to use the appropriate compiler. In this case, it's 0.8.0 or higher. So let's open the command line and let's run it and see what we get. But first, I promised I'm going to switch to a different contract because this one is a bit boring. I mean, the next one will not be too much. So here is a contract where I injected a bug. I just removed the plus equals and changed it into equal. So we will get a violation for our very, very basic and simple rule. So let's spin up the terminal, and I have a particular environment I use for the Certora CLI. And then what I type, maybe I'll increase this. Okay, what I'm going to type is simply Certora run, and then Certora confs the path to the config file, which in this case it was voting bag.conf, and in my case, I need to specify the path to the Solidity compiler, and I think I'm okay. And compiling, connecting to the server, and this is what you're going to get. You're going to get a URL where you will see the run report. The report will take a little bit of time. Let's see how long this will take us. So you can run it. I can show you what you're going to see. Okay, so this is the report live that is being is running now. I guess we're still queued. This is the status. Oh, okay, we're running already. Nice. Whoa, okay, we have results. So we have here the result of vote integrity. I'll increase things a bit, not too much. So we have here the results of vote integrity. As you can see, there's two rules here. The first rule is this n-free func static check. The prover actually checks that when we declare total votes to be n-free, it checks that it is indeed n-free. And that's okay, it is verified. The second thing is vote integrity, which is violated. So if we click on this, we see the message I wrote, total votes increases after voting, and this is violated. And now we click here, and we get a call trace. So I'll close the voting bug, the code, and in the call trace, you can see the entire trace of the calls. And on the right-hand side, in this case, you can see all the variables we have. For example, the message sender is, well, this is the address of the message sender. I won't try to pronounce it. This is, for example, the address of the voting contract. The value of is in favor is true. And for example, if I click on the assertion here, I see that the total votes is 1, and then votes before was 10, which is a violation. So I'll give you a minute to try and see if you can find out exactly where the violation is coming from on your own. If you didn't manage to run this or had any other problems, you can go to the lecture notes. And in the lecture notes in basics, there's everything I talked about. And there is also a link to a run where you can look at. It's probably the same or very similar example.
John, there's a question, if you can explain, does this work like a fuzzer?
So the answer is no, this doesn't work like a fuzzer. The idea here is that roughly speaking, the code plus the spec is all compiled together in some sense. And then from that, we generate basically what is a huge Boolean formula, or it's a huge Boolean proposition, if you want. And this Boolean proposition also has some variables, some integers, for example. So you get the Boolean proposition, x is greater than or equal to 1, and A is true and B is false, and all sorts of things like that. It's huge. And then we run what is called an SMT, which is satisfaction modulo theories. It basically tries to find if there is a way to satisfy this huge logical formula. If there is a way, that way is a counterexample. And if there isn't a way, we basically proved that this cannot work. So in essence, we are trying everything. If the rule passes, we actually prove that it works always. If the rule is violated, then we found a counterexample. So it's very different from a fuzzer, which ties a lot of different values. Okay, so let me show you. Let me show you one way you can find the violation. So in this case, we see that the total votes became 1, but the value of total votes before was 10. Now you can see it also in the global state. We have the storage state of all the contracts. In this case, we only have 1. And our message sender has not voted before, which is what we expect. The total votes is 10. And we have some number of votes in favor. It doesn't really matter in this case. And then we can see that we have the value of votes before. And we just have to go into the voting function and look at it. Now, what happens here is we can see that in this line, we have a store in total votes of a value of 1, which is suspicious because we should see 11. So we can click here on jump to source. And this will give us the actual source line, which is this line with our bug. So this was very simple and very trivial. So we can now move over to something a bit more interesting. So, before we continue, one extra thing. In the setup that we have here, and basically in the spec that we have, the prover will ignore any computation path that gets reverted. If we want to see also computation paths that get reverted, for example, cases where the message sender has already voted before and this will revert, we need to specify it in the spec. So by default, we ignore these computation paths. So the next thing we want to talk about is an invariant. So let me bring up the correct, the fixed voting contract. So if our contract is has no bug, then we know that the number of votes in favor plus the number of votes against should be the number of total votes. And this should always be true. So this is an invariant of the storage. And we can write it like this. Let's start a new spec. So the way to write it is fairly simple. Invariant, how shall we call it? Total votes is sum. Invariant. And then we simply write votes in favor. And we need the parenthesis because this is the getter plus votes against equals total votes. And you need here to convert total votes to a particular Certora type, which is a math int. Although those of you who very recently installed might not need, but most versions still need to convert. The reason why you need to convert it is because in order to avoid all sorts of cases where arithmetic operations overflow or underflow, the result of any arithmetic operation of integers in CVL is a type called mathint, which is unbounded. It never overflows or underflows. So the left-hand side here is mathint, and therefore we need to cast the right-hand side to math int as well, which is a sound operation. There's no problem here. And then here, if I want to use these things, then I need to declare all these functions as end-free. So, oh, sorry, that didn't work. Yeah, so we need to declare all these functions as end-free. And now we can simply run this spec. You can find the spec in Certora specs voting invariant. This is the spec, and we can simply run it and see what happens. So we have a config for this, and you can find that config under Certora conf and the same name, but .conf. So this is the configuration for it, and if you want, you can run it now. I'm going to skip this part and simply show you the result of running this on the correct contract. So new share, and this is the invariant part of the lecture notes, and we can open the report. So this is the report. As you can see, all the rules have passed. There's the end-free func static check. We checked all the three functions are okay. And then we have here the invariant. So an invariant, the way the prover treats an invariant is very much like induction. It starts at the induction base. So it looks at the state, at all the possible states after the constructor. There can be more than one. And it checks that the invariant, this particular line, holds after the constructor. And then once we have the induction base, we go to the induction step. The induction step is to assume that the invariant holds, and then run one of the possible functions. In this case, there's only one function we can run. And then after that, check if the invariant still holds. So in this case, we can see that, well, if the contract was more interesting, we would have a whole list here of functions, but in this case, there is only one function, and that is the vote function. Okay. So, so now we can look, maybe I should show you this on the Vim. Okay. So we have another buggy contract. It's in SRC voting bug 2. So here the bug is simply instead of +=1 votes against, we injected a bug which is simply =1. And your exercises are as follows. So you should try and write this invariant as a rule. Note I have here some, you might need to use require statement, which is explained here. It tells the prover to assume a certain condition exists. And then you should write the spec with the invariant and the rule on this contract, this voting bug #2 contract, and look at the report and find the bug. So we can give you a few minutes for that.
So which configuration, Sean?
There is a config which is called so you can use you can simply change the existing configuration since you're writing it. So the existing configuration is here, the voting invariant. and you can simply change the file to voting bug2 in order to use it. Oh yeah, I really need a button to play elevator music at these times. Shall we continue? Yeah, I think, okay, let's continue. So, so here is the solution. So to write the invariant as a rule, we need to use require. So we need basically an invariant has a precondition, which is this proposition, and a postcondition, which is the same proposition. So we have to to require beforehand that the votes in favor plus the votes against is equal to the total number of votes. And then we call the vote function, and then we assert that the invariant works. So this is the correct way to translate the invariant into a rule. Now, when we translate the invariant into a rule in this manner, we lack one important thing, and that is that it is not checked on the constructor. Now, the way it's written here, it's also not checked on any other function other than the vote function, but that can be remedied using parametric rules, which is something we will not touch in this tutorial. But this is the correct way to write the invariant as a rule. If you didn't have the precondition, something like this, then you will get a counterexample, as I will show you in a minute. So this is the solution. And let me show you the counterexample you would get if you did not write it like this. So here you have the solution in the lecture notes if you want to look at it. And you can see in the report the results, and that they both discover the bug. But let's look at the problem. Oh, sorry, let's look at what we get if we do not use the precondition. So without the precondition, if we use the rule but we don't have a precondition, we obviously get a counterexample. Now, or maybe it's not so obvious. So if we look at the call trace, this assertion fails. And you can see that votes in favor plus votes against is 17, but the total number of votes is 6. Now, the problem here is not in the voting function, or not only in the voting function. The problem here is in the storage. We already started in a state where the votes in favor plus the votes against is greater than the total votes. And the reason for that is the over-approximation of the prover. So this over-approximation means we assume more states than might be actually possible. And in this case, we assume there are more states than possible in this case. So even if we run this, in this case, we run on the correct voting contract, even in this case, the storage at the start of a rule can be anything. The only way to tell the prover no, you have to exclude certain cases from the storage at the start of a rule or at any point in the rule is by adding a require statement. We require that some things are impossible. And in this case, we missed that requirement. We haven't required that votes in favor plus votes against will be equal to total votes. And therefore, we started with this invalid state. Is that okay? Are there any questions, comments? Okay, so one last exercise about invariants. Can you find a way to inject a bug into the correct voting contract that will be caught by the invariant, but will not be caught by the rule, the correct rule, total vote is sum, the rule that I showed you with the precondition? I'll give you a few minutes to do that.
So there's the spec file with both the rule and the invariant, right?
Yes, the spec file with both the rule and the invariant is this one, voting bug to invariant.spec. You can open it here. It gives you in GitHub, and it's Certora specs, voting bug to invariant.spec.
And the conf file is the voting invariant.
Yeah, so the conf file has the same name. Yeah, I'm, as you can see, I'm very literal and bad in naming things. So it should be, sorry, this one should be voting bug 2. Yes, voting bug 2 is the config file. Okay, let's go on. So the solution is simply to add a constructor which breaks the invariant. So in this case, we have this I simply added this constructor, and this constructor breaks the invariant. It makes votes in favor be 1. So votes in favor plus votes against is 1, but total votes is 0. If you're unfamiliar with Solidity, in Solidity, all variables are initialized to the obvious value. So in case of integers, it's 0. And if you want to see the rule report, so we have that. We have a link to that on the lecture notes. So this is the solution, and here is the report. So as you can see, the rule total votes is sum actually is verified because it does not check the constructor at all, but the invariant is violated on the induction base because the constructor violates the invariant itself. Okay. So we're going to move over now to something a little bit different, and that is an ERC20 token. So an ERC20 token is a kind of money in the blockchain, a contract that behaves in some sense like a bank, if you want. So let's start writing a very, very minimal token. Right. Okay. So this is going to be a minimal token, and the first thing we need is to find out how much money, or to keep track of how much money each one of our clients has. So we'll have a mapping from address to UN256, public, and we'll call it balance of. This will give us the balance of various clients. So that's one thing we need. And then people need to be able to transfer money. Otherwise, you need to be able to pay. Otherwise, this money is pointless. So we need a function called transfer. So the transfer function transfers money from the message sender to the recipient. It transfers an amount of money. So this is how much money we are going to transfer. The message sender is the one losing money, and the recipient is the one gaining money. And of course, a more important function for us as a bank is the ability to deposit money. So we're going to need a deposit function. In this deposit function, the message sender will send us a certain amount of ETH, of Ethereum, and that's why this function is marked as payable. And we will give the message sender the same amount, well, an amount of tokens in return. So we get Ethereum and they get tokens. And the way we do it is basically we will set the user's balance to, well, we'll add an amount to the user's balance. So these are the two main functions. On top of that, there is a function called transfer from. The function transfer from, don't know, I hesitate to say it, but it's a matter of trust, or if you want contracts to work, sometimes the contract has to transfer your money into itself or somebody else. So you have a function like this. Sender is the person whose money we are taking. Recipient is the person who's getting the money, and amount is the amount of money that they're going to get. Now, not everybody can take money from other people and deliver it to somebody else or to themselves nilly-willy. They have to have allowance. We have to approve beforehand. We have to say, the sender has to say beforehand that they approve that the message sender can spend a certain amount of their money. So for that, we need another data structure, and that will be a mapping. And the first address is the sender or the person whose money we are going to use. The second address is the spender, the one who is allowed to spend the first guy's money or the first contract or person or whatever. And the last is the UINT 256. This is the amount of money they're allowed to spend, and we'll call it allowance. And now we need another function, which is approve, whereby the message sender approves that the spender will spend a certain amount of their money. So in this case, the message sender approves for the spender to spend their own money. Public returns. Cool. And this is the approve function. And last, we need the total supply. The total supply keeps track of how many tokens we have minted. Sorry, UINT 256 public total supply. This is the number of tokens we've minted. We create new tokens only in the deposit function, and well, I'm not going to implement any withdraw, so we don't need to decrease the total supply ever. But this operation is called burn, when you burn away a token and give someone something else in return. So you can see the entirety of this contract in SRC minimal token. So this is the entire implementation of this contract. It's a very, very reduced kind of token, an ERC20 style token. And we want to write some invariants for this. So we're going to write two invariants. Yep, good. So let's write a couple of invariants. The first invariant is a fairly simple invariant. So no balance for address 0. So address 0 is a special address in Solidity. It's basically no one's address, and if you send money over there, it's lost. So in this particular contract, I've prevented from transferring money to address 0 and from depositing money by address 0. Sorry, maybe depositing, did I? Oh, we'll see. And this is fairly simple. Balance of 0 equals 0. In CVL, we don't need to write address 0 as we would in Solidity. So this is one invariant. And the other invariant, we'll call it token solvency. And in this case, it refers to basically mainly the deposit function. So in the deposit function, as you can see, the message sender sends a certain amount. The amount of Ethereum sent by the message sender is msg.value. And our contract, the minimal token contract, receives this amount of Ethereum. And in return, or at least this amount of Ethereum, And in return, we add the same amount to the balance of the message sender and increase our total supply by the same amount. So this means that the amount of Ethereum we have should always be greater than or equal to the total supply. And if that is true, then we can actually implement a withdraw function where people can withdraw their tokens and get their Ethereum in return. So this is an important invariant. And to get the amount of Ethereum a contract has, we use native balances in CVL, and current contract is the current main contract that we are verifying. And this must be equal to total supply. So these are the two invariants we want to run. And we'll need, of course, to declare certain functions as n3. In this case, the functions that we need as n3 are the balance of and the total supply. So, okay. And this is the entire spec. You can see this spec in Certora specs minimal token.spec. Now this is the spec we're going to run. We have prepared a config file for it. The config file is under Certora conf minimal token.conf, and you can simply run it. If you don't remember, you just simply open the terminal. Well, if you have an environment for Certora, then use that environment and then Certora run and Certora conf minimal token.conf. And for me, I need solc 8.0. Okay. So now you have exercise. So we have here the report. And in this report, we can see there's a violation. And the violation is for the token solvency invariant. So after the constructor, the induction base, everything is okay. There's no problem. But we have a problem in the induction step. And as you can see, in the induction step, the prover checked all the functions. Well, all the functions that are not view functions, all the functions that can actually change storage. And it found a violation in the deposit function. And your task is to understand the violation and to fix the problem and rerun and see that the rule is verified after rerunning.
So you can continue. We have
Okay, so let's find the problem. So we look at the call trace, and well, I usually like to open this assertion to try and understand. So native balances is smaller by 1 from the total supply, but that doesn't help me much. So another thing is to look at the global state at the start. So our token has 3E36 Ethereums. And in the storage state, we can see that we have 3E34 total supply. So the total supply is less than or equal to the Ethereum balance. But if we look at by the end, you can see it either here in the assertion, or you can look at the global state after the assertion. You can see that the amount of Ethereum that the minimal token, our token contract has not changed. Now, there is one more giveaway here, one more hint to what the problem is, and it is the fact that in the native balances, we only have the balance of one address, and that's the minimal token. There's nobody else in this counter example. And that suggests that there's only one address acting here, and that is our own minimal token. So we can take a look, for example, here. This line is the sending of the Ethereum, and the sender is the token itself, and the receiver is the token itself, and it transfers 5. So from this, you can easily understand that the address calling the deposit function is the token itself. The token is depositing to itself. You can also see it here on the right-hand side in the variables. The message sender for this environment, this is the invariant environment, is that this is the env used to call the function deposit, is the minimal token itself. So the problem is that we are depositing to ourselves. This is not really an issue because we have the code of the minimal token. We know it's not going to do it. But it is part of the over approximation of the prover. The prover does not assume that this cannot happen. It does not assume anything like that. And therefore, we get this counter example. It is fairly safe to assume that the contract is never depositing to itself. We can see it in the code, but we can also add it to the code, and this is what we're going to do. Second. So we are simply going to add another require statement that the message sender is not address this, meaning it is not this contract itself. So we can see that in the code, and this file is minimal lending token fixed, and as you can see, we added here this line requiring that the message sender, this line requiring that the message sender is not address this. We cannot deposit to ourselves, and once we run with this, the violation will disappear. The rule will be verified. Okay, so the next step is to connect this to this minimal token to the voting. And the way we're going to do it is we are going to use the balance of the voter as the voting power. This is like this is very much like in shares. When shareholders vote, they use the when shareholders vote, the number of shares is the number of votes. So in order to do that, we need to know how many shares a voter has. So we're going to change the contract. I'm going to call it power voting. We need access to the token. So we want minimal token public token. So this will be our token. You can think of it as a pointer to the token. And we need, of course, to import the minimal token contract. We're using the minimal token fixed. And then here we need to do some very minor changes. So U into 56, the voting power is token dot balance of and MSG dot sender. This is the amount of voting power they have, and then we simply add to the total votes their amount of power, and the amount in favor or against is how much power they have. However, this can be a problem because if we simply use this, a person can vote and then transfer his money to some friend of his, and then the friend can vote with the same money. So the same money can be voted many times. So we don't want that. So what we're going to do is not allow it. And the way we're going to do it is we're going to keep their money for now until the voting ends. And when the voting is ended, they can get their money back. So this will prevent them to vote twice with their money while the vote is in progress. And to do that, we'll use the transfer from function. We're going to transfer from the message sender to our own contract the same amount of power. So now they cannot vote with it. Okay. And but we need to remember how much money we took because they'll want it back once voting has ended. So we need another data structure, and this will be a mapping from address to U into 56, how much money they used to vote, how much money we took from them. And we need to make note of that here. So amount voted for message sender, we're going to increase this by power. Actually, I can just use equal power because we don't let them vote twice, even if they have some extra money suddenly coming in. They won the lottery at some point. And we can also actually get rid of this total votes, because the total votes should be the balance of this contract, right? Assuming nobody decided to donate some tokens to us, yes? So let's remove this, and we can add a function, total votes, which is the total votes. It's the balance of this contract. So as long as nobody just gives us money for free or something like that, this should actually be our total votes. Okay. And if you want to see the full contract, you can see it in SRC power voting. So this is the full contract. I also added a function here, end voting, to end the voting, but I didn't bother implementing giving back people money because, you know, I don't have to. This is just an example, so we don't have to give them money. So let's write a spec. And instead of writing a spec, I'll do the lazy thing, and I'll simply use a spec that we already have. Well, not exactly. So in Certora specs, power voting spec, you can see two rules that we already saw before. The first one is integrity of vote. And this rule basically says, okay, we have the number voted, total votes before, and then somebody votes, and the number of total votes should increase because we ignore all the, or we haven't told the prover to consider also cases where the vote function reverts. So it will ignore all those cases. So somebody must have voted. And the second rule is this invariant, which we also saw before, which says votes in favor plus votes against equals total votes. So these are the two rules. Here at the top, we've declared these functions. To be precise, total votes is no longer a getter. In this case, it's an actual function. Now there's two more things here that I should mention. So the first thing is we have here this line, using minimal token as token. So this allows us to refer to the token itself. So maybe I'll show you the configuration. It will make things a little bit more clear. The configuration is in Certora conf powervoting.conf. This is the configuration file. And as you can see, in this case, we have two files in the scene, or two contracts. The first one is the power voting contract. We can omit the name of the contract if it is the same as the name of the file. And the second contract we added to the scene is the minimal token contract. So we have now two contracts in the scene. If you look at the verify line, power voting is our main contract or the current contract. But if we want to use the minimal token, we need this line, which says using minimal token as token. So token is now, in a sense, the instance of this contract. We also declared the function balance of minimal token as env3. So now you can write something like token dot balance of current contract equals something, and this will use their balance in the minimal token. So these are the two things. There's a third thing here, and that is this link. So if I remind you, let's get the minimal token contract here again. So this is the minimal, too wide. This is the minimal token contract. And if we, sorry, I need the power voting. I got confused. This is the power voting. Here we have token. So this line tells the prover that token is the minimal token contract. So the prover by default will create a single instance for every contract, just exactly one instance. And this line tells it to connect this variable in power voting with this instance, this unique instance of minimal token. So this is what we have. I've made a little illustration of this. Here's a minimal illustration of the situation. We have two contracts, power voting and minimal token, and the token storage variable in power voting is, in a sense, a pointer to the minimal token contract. So we can run the power voting conf that I've shown you before, and let me show you the results. Okay. So this is in the lecture notes under power voting. Here we have the spec, which I've showed you. And here is the report after we run the power voting conf. And as you can see, there is a violation here in the vote integrity. So the invariant is satisfied. It is verified. That's the correct way to say it. However, the vote integrity fails. And your exercise is to find the violation. And the problem is with the vote integrity rule itself. So you need to fix it so it would consider all possible cases and rerun it and check that the rule now passes. You need to use, well, you might want to use the logical operator of implication, this logical operator, which means if the left-hand side is true, then the right-hand side is also true. And just a technical useful thing, you can have several asserts in a rule, and the prover will verify all of the asserts. So instead of having one big condition with a lot of and operators between the sub-conditions, you can just have several assertions. So I will let you have some time to try and solve this exercise. And yeah, I like to share this because I'm very proud of my illustration. Okay, so since we're running short of time, I'll present the solution. So let's look at the rule report. So this is a rule report, and the reason the rule was violated is because a rule is wrong. And the rule is wrong, you can see it, well, I know the answer, so I'll go straight to the source. Our voter, 8200, has 0 tokens. So our voter voted with 0 tokens. You can see here, EMSG sender is 8200. This is our voter. And they voted with 0 tokens. And therefore, obviously, the total votes should not have increased. I mean, nothing happened. Their power is 0. So we forgot how to, we forgot this to treat this case. So if you want to treat both cases, the case where a voter has non-zero power and the case where a voter has 0 power, you need to add it into the rule. And the way to do it is the following. So you can also see the answer in the lecture notes if you want. So first we have U into 56. Let's call it balance power. Balance equals token dot balance of EMSG sender. This is the amount of money that the voter had before voting. And then we can say if the balance was greater than 0, then the total votes must have increased. And let's copy this. We can add another assertion saying if the balance was 0, then the total votes should not have changed. And we can have some meaningful message here, which I will skip. So this is it. I think we want to leave a few minutes for questions. So we won't go over anything else. Okay. So you can continue with the lecture notes on your own. And let me know if there are any questions, comments in the chat.
Yes, and if you have any questions and you want to open the microphone, let us know. So we can enable the microphone for you.
Thank you. Also, if you have any feedback on the seminar, stuff that we missed, stuff that you preferred, sound quality, haircut of the presenter, I don't know, anything.
So any advice on how to be good at formal verification? You have a question on that? You want me to answer?
That's a tough question. I always think so formal verification and in particular CVL is much closer to declarative programming or functional programming. So you need that sort of switch in your brain. So the usual programming is imperative programming. You say, you tell the computer, do this, go here, print that. Declarative programming is more difficult. I have, it's more like mathematical proof. So I have some integer, I have some mapping, which should satisfy a certain condition. Yeah, I don't really know Haskell, but I think from what I understood from other people, yeah, if you're good at functional programming, that would be very helpful here.
Really think symbolically, I agree. So you really need to almost do it in your head first. And practice a lot. It's just, and like any other tool you are using or framework you're using, you can practice. There are many tutorials that we provided.
Before leaving, I wanted to share the link to the Uniswap contest for those who want to join. Here it is. You can find it on the chat, and we also switching microphone is not allowed. I'm gonna allow the microphone option. Give me a second. You should turn on your. You can turn on your microphone now if you want to.
Yeah, sure. Is there any community like Discord community to meet like-minded people in formal verification?
Yeah, so we have our own Discord. You can reach it from, well, both from the Certora website and the Certora documentation. Let me see if I can actually link to it in the chat.
Sure, thank you.
Okay, can we?
From any wool report that we provide.
Oh, yeah, I forgot about that. Let me share the screen then. That'll be easy. This is it. We have a rule report, right? Yeah, so we have our Twitter. There's the documentation. Here is the Discord. Here's
Sure.
the Certora Discord. Yeah, I'll post this in the chat. I don't know if this, yeah, it should work, I guess.
It's in the chat.
Ah, okay.
Thank you.
Do we have any more questions? Feedback is welcome as well. Anything you want to tell us?
Okay, so thank you very much for attending. Fiorella, do you have any closing?
Now I think we are done. Thank you so much for joining. Hope you guys join the contest this week. The original date was on the 4th of September, but they changed it, and now it's on the 6th, which is better because we have more time to prepare. So hope you all join, and thank you for joining today. See you around, everyone. Bye-bye.